That IMVC is going to cancel this one, and we will get the following. Minus I have RIL times RL squared. In this case, what can you say about the sign of this function? So this function, as you see, R of IL is always positive. Okay? So minus R of IL is always a negative number. Okay? So in a closed neighborhood around equilibrium point, what can we say about the sign of this function? So we have VC IL here, and let us say that I'm looking at this function in a small neighborhood around the equilibrium point. Okay? So here, when I look at this function here, this thing is always negative, and this can take values either positive or zero. So in a small neighborhood around the equilibrium point, do you think I can say something definite about the sign of this function? What can I say about the sign of this function? It is going to be negative or zero. Okay? Obviously, at the equilibrium point, this function is zero. Okay? Because IL and VC are all equal to zero. Okay? So I know that the function is negative everywhere except the origin. But is it zero somewhere else in this ball? So can this function take zero value anywhere other than the origin in this ball? And this function takes zero value anywhere other than the origin in this ball? Yes, if IL is equal to zero, and in that case, if IL is equal to zero on this line, the function is always equal to zero, and it's negative everywhere else. Okay? So such a function is going to be called a negative semi-definite function. Okay? We will actually define these negative semi-definite functions. If the function was only equal to zero at the equilibrium point, and if it was negative everywhere else, it would be a negative definite function. Okay? Now, because it can take zero values at some places other than the origin, we will call the function as a negative semi-definite function. Okay? And in that case, I see that V dot of x is actually smaller than or equal to zero for any x in the state space. So what does this type of fact tell us in terms for the trajectories of the system? Do you think that around the equilibrium point, the trajectories of the system, do you think they can get away from the equilibrium point? So, do you think a trajectory of the system can look like this? In this case, it really cannot. So, because here, if there was a trajectory looking like this, then V dot should actually be positive in that case. Because on this trajectory, I see that V is clearly actually increasing. Because we are crossing the level curves with increasing C values. That actually means that such a trajectory of the system is not really possible. The trajectories of the system, when I start a trajectory, such trajectories would either remain on these level curves, it is V dot is equal to zero case, or they're trying to move inside. Alright? But that is actually what is happening. So now, if I ask you the following question. Given an epsilon ball around the equilibrium point, okay? Given an epsilon ball, an arbitrary epsilon ball around the equilibrium point, can you find me a delta ball such that when I start the system in that delta ball, the whole trajectory of the system is going to be inside the epsilon ball? Given any and if when you start in that delta ball, when you start the system in that delta ball, the system trajectories will remain inside the epsilon ball. Can you find such a delta ball for this system? And the answer is actually is actually yes. So here, when I look for that delta ball, for example, if I start with such a delta ball, okay? When I start with such a delta ball, I know that because I start the trajectories of the system in this delta ball, I know that the trajectories will never be able to cross this level curve outside the delta ball. So here I can choose my delta ball as this green ball, and to actually show that the trajectories will actually never leave the epsilon ball, because in that case when I start a trajectory somewhere in this delta ball, the trajectory will never be able to cross this level curve that is encircling this delta ball, because if it goes outside the level curve, that is going to mean that V dot is going to be positive somewhere on that trajectory. Because V dot cannot be positive, I could actually conclude that for any such epsilon ball, we will be able to find a delta ball actually that would be satisfying the stability condition. So the conclusion from this type of analysis is therefore the equilibrium point Xc is equal to 0, 0 is actually stable in the sense of Lyapunov. Okay? We could conclude stability based on the sign of V dot using this auxiliary function. If V dot was negative definite, in such a case, we would be able to conclude asymptotic stability as well as stability. In this case, we won't be able to say anything about the asymptotic stability based on V dot here. But if it was positive, if it was negative definite, if it was actually negative for all x non-zero, in that case we would say that V dot is negative definite, and in that case we would be able to conclude that the equilibrium point is not only stable but also asymptotically stable. But currently I really cannot say that, because V dot is negative semi-definite here only. So we won't be able to say anything about the asymptotic stability based on this analysis. In this case, this is not correct. So as you see here, these functions are extremely important in Lyapunov's direct method. That is why we're going to be now defining them in a formal way. So we will define what it means for a function to be positive definite, positive semi-definite, and we will furthermore classify those definitions based on locality. So we will have a locally positive definite function or a globally positive definite function. They will have different properties. Let us write positive, negative, semi-definite functions. So I will start, so here, positiveness or negativeness, I will define only the positive functions here. If you would like to learn about the negative definitions of negative or negative semi-definite functions, then you would replace the definitions, the greater signs in the definitions, by smaller than signs. Okay? So I will only give positive semi-definite or positive definite function definitions. So let us write our first definition. A scalar valued function, scalar valued continuous function. It is important for these functions to be continuous. Continuous function v of x of the state vector x is said to be locally positive definite. if, or since this is definition, it might be if and only if actually. There are two properties. V of 0 is equal to 0 and V of x is positive for all x in BR minus 0, where BR is a ball of radius r larger than 0 around the origin. Okay? So here, if I define BR formally, it's looking like this. This is the BR definition, and this notation BR backslash 0, it is set subtraction. Okay? BR minus 0 is nothing but the set minus the origin. Okay? So this is nothing but a ball. So if I try to show BR minus 0 set here, it is actually going to be a ball in the state space where the 0 element is actually excluded. Okay? So BR minus 0 set is actually looking like this. So this is local positive definiteness. A function is called locally positive definite if there exists a BR, if there exists a ball around the origin which would satisfy this property. In that ball, V of 0 should be 0. So the function should have 0 value at the origin. And in that ball, everywhere other than 0 the function should have positive value. So now if I look at an example, let us say that V of x is the following. X is here. In all of these examples, x is x1, x2 transpose. Okay? V of x is, let us say that x1 squared plus x2 squared times sine of x1 squared plus x2 squared. Okay? So now if I look at this function, can you tell me that in the whole state space, do you think this function will be always positive or 0? No, because here this part of the function is maybe this part is going to be always positive, but I know that sine will be able to take negative values. Okay, if x1 squared plus x2 squared is large, if x1 squared plus x2 squared is for example larger than pi, in such a case, sine function will take values which are negative. That means that this function will not be actually a globally positive definite function because it will take some negative values. I need to constrain myself in a small ball around the origin for this function to be positive definite. That is what locally positive definite, being locally positive definite mean. So if I will not be able to make this ball arbitrarily large actually, okay? So this ball should have some limits. So now suppose that I have constrained myself in a small ball around the origin, okay? Suppose that I'm satisfying this inequality, x1 squared plus x, let us say that x1 squared plus x2 squared is actually smaller than pi. Okay? Suppose that I have this property. Okay? In such a case, I can for example choose my epsilon ball here like the following. Let us say that this ball BR let us say that r is equal to square root pi over 2. Okay? If I choose r square root pi over 2, I know that this inequality is actually going to be satisfied. Okay? If I choose r to be square root pi over 2, or anything smaller, actually anything smaller than square root pi will do for us. Okay? So here, but if I choose r is equal to square root pi over 2, I know that this function, this sine function would always be positive. Okay? In such a case, in this ball, the sine function is always going to be positive. When the sine function is positive, what can you say about the signs of the overall function v of x in this ball? In that case, when the sine function is positive in this ball, what can you say about the sign of this function in that ball? It is going to be positive everywhere other than the origin. Okay? That is why we can actually call such a function as a locally positive definite function. In a small ball around the origin, it is going to be locally positive definite. It is not going to be globally positive definite because I cannot make this ball arbitrarily large. If this ball is large, the function is going to start taking negative values. In such a case, I won't be able to claim actually global positive definiteness. The function is only locally positive definite because positiveness is only valid in a small ball around the origin, not everywhere. Okay. So this actually brings us to the definition of the globally positive definite function. Scalar valued continuous function v of x is said to be globally positive definite. If v of 0 is equal to 0 and v of x is positive for any non-zero x. So in this case, we are not really looking for a small ball around the origin. The function should be positive everywhere other than the origin. So here, in this definition, what we do is that we let r go to infinity. Okay? If we let r go to infinity, if that property is still satisfied, then we can say that the function is globally positive definite. So when I look at an example, then it is going to be the following. So v of x, I can just remove the sine function there, x1 squared plus x2 squared. Okay. We know that this function is actually 0 at the origin and it's positive everywhere else. Okay? And in such a case, I can actually call this function a globally positive definite function. And this function is locally positive definite. One of the definitions is stronger actually. So if a function is globally positive definite, it is at the same time locally positive definite. Okay? So if we have a function which is globally positive definite, then that would imply locally positive definite property. Okay? But the reverse implication is not correct. Okay? If there is global positive definiteness, there is also local positive definiteness. But reverse is not correct. And the example is this one. This is not globally positive definite clearly. Now I can look at semi-definiteness. So as I told you, if you are wondering about the negative definite, locally negative definite functions, what you have to do in these definitions, you just change the greater than signs with smaller than signs, and that will give you the related properties. So let us look at positive semi-definite functions. A scalar valued continuous function v of x is said to be locally positive semi-definite. If we have the following, v of 0 is equal to 0, this condition is should always be valid, and we have v of x is larger than or equal to 0 in BR for all x in BR, let's say. Where BR is a ball of radius around the origin. In this case, I don't have to exclude actually the origin from the definition, because in the earlier case we were looking for positivity, and this 0 was not satisfying positivity. But here we are looking at non-negativity. Okay, so and this the value of the function at the origin is already satisfying this inequality. Okay, that is why from the ball I really do not have to exclude 0 in positive semi-definiteness. So here we are saying that a function is actually a positive semi-definite, and it is a local positive semi-definite function if and only if we could find a ball around the origin such that in that ball the function is always non-negative. It always has non-negative values. So here I will write the following function. V of x is equal to the following: x1 squared 1 minus x2 squared. It is this function. So now the question is, will we be able to find a ball around the origin such that the function would always have non-negative values in that ball? Okay. So here, if I look at this function, do you think this function is always positive in the whole state space? Is it always non-negative? Do you think? No, it can take negative values as well. Okay. So that actually means that I need to constrain myself in a small ball around the origin. So let us say that I'm looking at the following ball. Let us say this ball is a ball of radius 1 over 2. Okay? Minus 1 over 2. 1 over 2. Minus 1 over 2. Let us we are looking at B1 over 2. A ball around the origin with radius 1 over 2. In that case, I know that because x2 values takes values only between minus 1 over 2 and plus 1 over 2, this term would always be positive in that case. In this ball, this term will not be able to change the sign. Okay? And this is true for any ball with radius smaller than 1. Okay? So 1 over 2 is just one example. Okay? So this is always positive in this ball, and I know that x1 square is always going to be non-negative. Okay? I know that the function is 0 at the origin, and x1 square is always non-negative. The question is, can this function take 0 values in this ball other than at the origin? Okay? So can such a function take 0 values in this ball other than the origin? Yes, if x1 is equal to 0, for example, the function is going to be 0 everywhere on the x2 axis. Okay, and I see that the function will actually take 0 values some other places than 0 in this ball. That actually means that the function can only be positive semi-definite, not actually positive definite. Okay? Because it takes values, takes zero values at some other places than the origin. The function can only be positive semi-definite, not positive definite. And it is locally positive definite because this is going to be true only in a small ball around the origin. I cannot make this ball infinitely large. When I try to make this ball infinitely large, the function can take negative values as well. That is why such a function is always called a locally positive semi-definite function. Okay?
Why does VR have to be a ball? Can't it be like a...
It actually, in a general definition, this can be any norm. You can actually replace this by any norm definition. For example, you can define x as, here we are defining it as x1 squared plus x2 squared given like this, but you can actually replace it to an L1 norm looking like this. In that case, this ball would be a diagonal region. Or you can replace it to an infinity norm, which is the maximum of x1 and x2. In that case, this is going to be just a square. Okay? So in general, by replacing this norm definition with other norms, you can come up with other parts. But all of them are going to be equivalent actually. If I can find a diagonal region around the origin which would satisfy this property, I will always be able to find a circular region in that diagonal region. Okay, so all of the definitions would come to the same thing. They would be equivalent actually. But here one thing is important. Your region definition should consider all of the directions here. Okay, so you cannot really discard one of the directions. In that case, the conclusion is going to differ. You can take an arbitrary region looking like this, but the radius of this curve should be positive in all directions. Okay, as long as you take it, as long as that radius is actually larger than 0 in all directions, you can use an arbitrary curve.
We can define this as like bounded from x2 by 1, and then x1 can go to.
Yes, you can actually look at these elliptic. You can actually look at such elliptic regions. Yes. No. So let us write our final definitions. So here I will replace this. A scalar valued continuous function v of x is set globally positive semi-definite if v of 0 is equal to 0 and v of x is larger than or equal to 0 for all x in the state space. Okay? That is the definition. So in this case, I can make this ball arbitrarily large here. Okay? So I can let R go to infinity and the property should be satisfied for global positive semi-definites. So here I can look at an example. V of x is equal to x1 squared. In this case, I know that the function is 0 at the origin. The function is 0 at the origin, and it is non-negative everywhere. But it is not positive definite because the function can take 0 values somewhere other than the origin. Okay, the function is 0 on the x2 axis everywhere. Okay. But That is why it really cannot be globally positive definite. Okay? It is only non-negative everywhere in the state space. That is why such a function is globally positive semi-definite. In this case, I can make this ball that I have found in the earlier case infinitely large. That is why this is a global property. Now let us look at some examples. V of x is equal to minus x2 to the power 4. What is the best descriptor of this function in terms of what we have learned? We see that the function is negative or non-positive. This function is non-positive everywhere. Okay? So, what can I say about the positive definiteness, negative definiteness of such a function? First of all, because the function is actually non-positive everywhere, I will be able to say a global property. So this is globally, what should I say? Negative definite or negative semi-definite? If it is negative definite, it has to be negative everywhere other than the origin. Okay? So can this function take zero values other than the origin? Yes. That is why this is going to be a negative semi-definite function. This is globally negative semi-definite. What can you say about such a function? First of all, the function is not always positive or negative in the whole state space. That is why I have to constrain myself in a small ball. Okay? So whatever property it is, it's not going to be global in terms of. In a small ball, can you say that this function is non-negative, non-positive, or positive, negative? Can you say? It has mixed signs in any ball. Such a function is therefore called an indefinite function. A sign indefinite function in that case. You can actually say something like that. Yes. In general, because for these functions, actually, it is defined at the origin. But if the equilibrium point is somewhere else, then you have to define those balls around the equilibrium point. Because we can always define a new state variable that would pull the state at the origin, the definitions will be sufficient to be around the origin. But if you have an equilibrium point somewhere other than the origin, the functions has to be defined around those centers. Okay. Yes. Yes, exactly. For example, if I look at this, v of x is equal to 1 for all x. This is not a positive definite function, okay? Because it's not zero at the origin. Okay? So this is not positive definite. It cannot be called positive definite. We want the level curves to be closed curves around the origin. We want always the level curves that are looking like this. Okay? So if we have a continuous function, if it is 0, 0 at the origin, and if it is positive everywhere else, the level curves around the origin would always be looking like this. I really do not want level curves that are actually looking like such curves. Okay, I want to be able to equate the convergence of the trajectories to the origin to the function getting smaller and smaller. Okay, that is why we always want level curves of the function around the origin as closed curves. The shape really does not matter, but we want the level curves to be closed curves like this. If the function is 0 only at the origin, and if it is positive everywhere else, and if the function is continuous, the level curves of that function would always be looking like these closed curves when we get very close to the origin. Okay, that is why we are actually defining it in that way. V of x is equal to minus x1 minus x2 to the 8, 5 minus x1 squared minus x2 to the 4. What can you say about this function? This is globally indefinite. What can you say in a small ball around the origin? Globally it is indefinite, okay? But what can you say in a small ball around the origin? If we are in a small ball, then this term would always be positive. If we are in a small ball around the origin, this term would always be positive, okay? What can you say about this? This is going to give a negative semi-definite function in a small ball. So what is our conclusion? Locally, negative semi-definite. Because the function can take zero values somewhere other than the origin, it is negative semi-definite. And finally, I have v of x is equal to minus x1 to the 4 plus x2 squared times 5 minus x1 squared minus x2 to the 4. What can you say about this? Again, globally, I won't be able to say anything. Why is that? Because this is going to change its sign globally, okay? But if you are in a small ball around the origin, then this term would always have the same sign. It is going to be positive. And what is the property? Local or global? It is locally negative, okay? Because it is 0 only at the origin, it's negative everywhere in a small ball around the origin. Which completes this lecture. Thank you very much. Yes. We can always move. If equilibrium point is at some non-zero position, we will first change the coordinates so that equilibrium point is at the origin. In that case, we will have z variables, and we will be able to define these functions in terms of the z variables, so that they are going to be defined around the non-zero equilibrium point. Hiçbir şey fark etmeyecek.
Eksi 1 ile eksi 1 eşit olduğu ve hani toplamların 5'lik bir yer var mesela.
Var.
Topu o şekilde aldığımızda mesela.
Ama yeterince küçülttüğünüzde o
Yani
yes, there exist olması gerekiyor.
Şu aşağıdaki örnekte negatif semi-definite dedik ya.
Aha.
Öbüründe negatif definite dedik zaten.
Evet.
Aradaki semi farkı nereden?
Şu şöyle, x1 ile x2 eşit olduğunda ben kendimi küçücük bir bolun içine hapsettiğimde burada, şu her zaman pozitif oldu. Kendimi küçücük bir bolun içine hapsedersem şu terim origin dışında bir yerde sıfır oluyor mu olmuyor mu ona bakmam lazım. Tamam mı? Şu terime. Şimdi şu terim her zaman negatif. Originde de sıfır. Ama origin dışında bir yerde sıfır oluyor mu? Olmuyor mu? Önemli olan o. Bu aslında oluyor. Yani çünkü x1 x2 eşitse şu line üzerinde bu arkadaş her zaman sıfır. O zaman demek ki bu origin dışında her yerde bu topun içerisinde negatif olamaz. Sıfır olduğu yerler de var. Dolayısıyla şu semi oradan geliyor. Burada ise kendimi küçük topun içine koyduğum zaman origin dışında her yerde negatif olmak zorunda.